Motion of a charged particle in a magnetic field. Consider a region where there is a magnetic field. Here the magnetic field is along the negative Z direction. That is, the magnetic field lines are perpendicular to the screen and pointing inwards. Now, if a charge having magnitude q enters this magnetic field with a velocity along the x direction, it is seen that it starts moving along the circumference of a circle. And it keeps on moving along the same circular path. Why it moves along the same circular path? So when a charged particle enters a perpendicular magnetic field, it is in that the charged particle moves along the circumference of a circle. Let us see why it moves along the circumference of a circle, or why it follows a circular path. Now let us see why a charged particle with certain velocity v enters a perpendicular magnetic field, executes a circular motion, or why it follows a circular path. As we have discussed, a moving charge in a magnetic field experiences magnetic Lorentz force. Here in this case, the angle enclosed between the direction of velocity vector and magnetic field vector will be 90 degree. Therefore, the magnetic Lorentz force will be F is equal to QVB sine 90 degree. Since sine 90 is equal to 1, we have F is equal to Q into V into B. This is the maximum Lorentz force experienced by a moving charge. So, a moving charge, when it enters a perpendicular magnetic field, experiences the maximum magnetic Lorentz force. And we have also seen that the magnetic Lorentz force is always perpendicular to the plane containing both velocity vector and magnetic field vector. Meaning, the magnetic Lorentz force will be perpendicular to velocity vector and magnetic field vector, which is shown there. Therefore, this force cannot change the magnitude of velocity, but it can change only the direction of velocity. So due to this magnetic Lorentz force, the particle will deviate from its original straight line path, and it reaches another point where the particle will have the same magnitude of velocity, and the velocity will be again perpendicular to the magnetic field. Hence, the magnetic Lorentz force will be again perpendicular to velocity vector and magnetic field vector. Therefore, the particle again deviates from its path and reaches the third point, fourth point, fifth, sixth, etc. Now, if we collect all these points together, or if you trace out the path followed by the particle, it will be a circle. So the particle executes a circular motion. Here, the necessary centripetal force for the circular motion is provided by the magnetic Lorentz force. If we have a particle of mass m with a velocity v moves along the circumference of a circle having radius r, then the necessary centripetal force for it is mv square by r. Here this mv square by r is provided by the magnetic Lorentz force QVB. So we have mv square by r is equal to QVB. Rearranging, we get velocity equals QBR by m. which is a constant. That means the speed of the particle is constant. Therefore, the particle will be executing a uniform circular motion. If a particle executes a uniform circular motion, then we can define its angular velocity by the equation v by r. Substituting the value of v from the above equation and solving, we get omega is equal to qb by m. Since it is uniform circular motion, it will have certain periodicity. Therefore, the time period of motion, circular motion, will be t is equal to 2 pi by omega, which is 2 pi divided by omega is qb by m. So 2 pi divided by qb by m, that is t is equal to 2 pi m by qb. That is, every after t units, capital T units, the particle will complete one circle, one full circle, or one cycle, or one revolution. So t is called the time period of motion, circular motion. The reciprocal of time period gives you frequency. Frequency nu equals 1 by t, which is reciprocal of time period, that is qb by 2 pi m. This is the working principle of the particle accelerator called a cyclotron.